Hey everyone. Today we introduce a random walk, one of the most fascinating objects of study in probability theory. A random walk is just a walk that changes directions all the time at random. Imagine you flip a coin every second, and depending on the outcome, you either step to the right or step to the left, and then you repeat. So eventually what you're doing becomes a random walk. Let's express it mathematically. A random walk is a walk on integers, 0, 1, 2, 3, -1, and so on. Imagine that a particle initially is placed at some location, let's say k. Each second, the particle moves one step to the right, to k plus 1, or to the left, to k minus 1, independently, and with probability 1/2. A number of interesting problems can be asked about this model. We will consider a problem that's called the gambler's ruin. What's the probability that the particle that makes a random walk reaches some target location, n, before it reaches 0? We can imagine this being a suicidal person. If she reaches 0, she would fall down the cliff. And if she reaches n, she would be taken to safety by an ambulance. So what's the probability that that person will be saved? Or you can think of a gambler who initially has k dollars and starts to bet. Every time he may win $1 or lose $1. So the person's winnings are making a random walk here. What's the probability that the gambler ends up with n dollars before he goes bankrupt? Solving this problem directly is difficult because there are so many scenarios, so many possible ways to make the walk. A conditioning trick helps. Specifically, we will condition on the first step of the walk, whether it is to the right or to the left. And we will compute the probability of this event. Let's call it EK, indicating that the walk starts at location K, by using the law of total probability. Probability of EK is the conditional probability given that the first step is to the left, times probability that the first step is to the left, plus the conditional probability given that the first step is to the right, times the probability that the first step is to the right. These probabilities are both 1/2, according to the rules. What is this probability? Here we assume that the walker makes her first step to the left. After making that step, the walker will be in position k minus 1. From that time, the walk resets. The question remains the same. What is the probability of reaching n before reaching 0, but now from a new starting position, from the position k minus 1? So this probability is P of E, but k minus 1, which indicates that the starting position is now not k, but k minus 1. Similarly, what's this? Here we assume that the first step is to the right. After making that step, the walker is now at position k plus 1. The goal is the same, reaching n before reaching 0, but now from the position k plus 1. So this probability is P of E, but with the new starting position, k plus 1. So if we denote, for convenience, the probability of EK by PK, this equation becomes PK equals 1/2 PK minus 1 plus 1/2 PK plus 1. And this equation holds for any starting position K, 1, 2, n minus 1. What else do we know? We know P0. P0 is the probability of reaching n before reaching 0 if you start from 0, but that will never happen. You will never reach n. You already add 0. So P0 is 0. What's Pn? Pn is the probability that you reach n before reaching 0 if you start at n. But if you start at n, you have already reached n. So the probability is 1. So this becomes a system of linear equations. There are how many? N minus 1 plus 2. There are n plus 1 linear equations in how many variables? P0, P1 through Pn in n plus 1 variables. We can put it in the computer and solve it. However, it would be actually easier to solve it directly without using any computation. This equation is so beautiful. It tells us that pk is the midpoint between pk minus 1 and pk plus 1. Let's plot pk. X-axis is k and y-axis is pk. If this is pk minus 1 and this is pk plus 1, where is pk? According to this equation, pk will be the midpoint of this interval that joins pk and pk minus 1. But that happens for any triple. So I can do pk plus 2, for example, and that point must be the midpoint between these two. And I can continue it to k minus 2, and that point must be the midpoint between these two, and so on and so forth. So all these equations, all they tell us that all these points lie on a line. The dependence is linear. These boundary conditions tell us that P0 is 0. So this is the point P0. And that Pn is 1. So we just need the equation of the line through these 2 points, 0, 0, and n, 1. That equation is k over n. Let's check it. P0 is 0 over n, 0. Pn is n over n, which is 1. And this equation is linear. So this is indeed the solution to this system of equations. And that is the answer. The probability that a random walk starting from position k reaches n, safety, before reaching 0, a disaster, equals k divided by n. Now we solve another problem that may not sound like a problem about random walk, but it is so. Teams A and B, who have equal strength, play against each other continually. 1 point is awarded to the winner of each game. The first team that leads by 5 points wins the tournament. Suppose that Team A currently leads by 1 point. So it has a slight advantage over Team B. What is the probability that Team A wins the tournament? We assume also that the outcomes of each game are independent. To solve this problem, we can realize it as a gambler's ruin problem, as a problem about a random walk. Indeed, let's consider the lead of A, the number of points Team A leads. Initially, it leads by 1 point. Let's plant a flag indicating the lead of A. Then at each game, either Team A wins that game, and in that case, the lead of A increases by 1 point. So this flag gets replanted 1 step to the right. Or Team A loses that game, in which case the lead of A decreases by 1 point. So this flag gets replanted 1 step to the left. Because teams A and B have equal strength, the flag gets replanted to the right or to the left with probability 1/2. Because the games are won or lost independently, each step is independent. Therefore, the lead of A, this flag, is doing the same simple random walk that was described in the previous problem. According to the rules, the game ends when the lead reaches either 5, in which case Team A wins, or -5, in which case Team A loses. We're interested in finding the probability that A wins the tournament. This happens if, starting at 1, the lead reaches 5 before reaching -5. This becomes very similar to the gambler's ruin problem that we considered before, except that problem was about reaching something before reaching 0, and we have -5. So what do we do to make it exactly the same as gambler's ruin? We shift the entire picture by adding 5 to all the numbers. That will make -5 0, and we will have an exact match to the gambler's ruin. -5 becomes 0, 5 becomes 10, 1 becomes 6, and so the equivalent formulation is what's the probability that starting at 6, the simple random walk reaches 10 before reaching 0. This is the gambler ruins problem that we solved. And the solution, which I'll show, is that this probability is k over n. In our case, k is 6, the initial location, and n is 10, the target location. So the probability is 6 over 10. And the answer is Team A wins with probability 60%. Random walk is a fascinating object. A lot of other interesting questions, deep questions, can be asked about it. For instance, what is the average time of such walk? What's the average number of games in such tournament? What about the biased random walk? What if the teams don't have equal strengths and you move to the right with probability 0.6 and to the left with probability 0.4? What is the probability of reaching 0, the bankruptcy, eventually, whether or not you reach n in the meantime? This walk was on the line in dimension 1. What about two-dimensional walks or three-dimensional walks, where at each step you can move to the right, to the left, forward or backwards? What happens if you make a walk with smaller and smaller steps? In the limit, such walk becomes kind of smoother. Is there an analog of such walk in continuous time, where at every instant you change directions? These are valid and very interesting questions, and I hope you will have fun reading more about random walks and related topics. Stay with me, have fun.